Hey everyone, welcome to this conversation today, which is going to be in the areas of quantum computing, artificial intelligence, and all the myriad issues that these subjects bring up. And we're going to be speaking really with one of the world's great expert in these areas. It's Scott Aaronson, and Scott is the Schulenberger Centennial Chair of Computer Science at the University of Texas at Austin, and he is the founding director there of the Quantum Information Center. He is a theoretical computer scientist who has made significant contributions to the fields of quantum computing and computational complexity theory. He has also spent, relevant to part of our conversation, that we will have 2 years working as a guest researcher at OpenAI, where he focused on AI safety. And he joins us now from his home in Austin, Texas. So welcome, Scott. Thank you for joining this conversation.
Thanks so much. Great to be here.
So, Scott, I just wanted to start by asking, there's a lot of talk, at least in the popular press, general public, about quantum computing as, leading to an exponential increasing computational power, flattening every possible computational problem that one might imagine. That feels very overblown compared to my understanding of what quantum computers can, in the best of worlds, do. Can you just sort of take us through your take on how the public should really think about what quantum computers are capable of and what they will do?
Yeah, so it's a way to exploit the laws of quantum physics to solve certain specific problems much faster than we know how to solve them with conventional computers. Okay, so I think a key point for a layperson to understand is that it's not just a general purpose accelerator of everything. Quantum is not just a synonym for awesome. Right. If you want to get an advantage from a quantum computer, you have to exploit the way that quantum probability works differently from classical probability, right?
Yeah.
That it involves these numbers, these amplitudes that can cancel each other out, that can interfere with each other. This is the trick. This is the one trick of nature that we get to exploit that a classical computer doesn't have. And it's really for problems with a very, very particular structure that we know how to get a dramatic speed up over a classical computer using that trick. The two biggest examples here are the simulation of quantum physics and chemistry themselves. That was the original application that Richard Feynman had in mind when he talked about this 40 years ago. And that's probably the most important application economically, even to this day.
So you're saying actually just look at some real quantum system and don't try to simulate it using classical computers, but actually have the processes in some sense simulated in the right way by the right kind of physics.
Exactly. In some sense, that's what a quantum computer was born to do. Now, a huge discovery in the 1990s that made a lot more people interested in quantum computing was the famous discovery of Peter Shor, that a quantum computer can also give huge speed ups for certain problems that have nothing to do with quantum mechanics. And that among these are breaking the public key encryption systems that currently protect the internet. Okay, and a quantum computer could do that by, for example, quickly finding the prime factors of huge composite numbers, solving other problems in number theory and group theory that underlie modern cryptography. Okay, but it's crucial for people to understand that in order to develop those algorithms, Peter Shor had to take advantage of very, very special properties of these problems, factoring and so forth. And we don't know how to get the same kind of speed up for most of the problems we care about in computer science, like training neural networks or financial portfolio optimization or DNA sequence alignment, for all sorts of problems like that, we typically know how to get more modest speed ups from a quantum computer. And it will be longer before those speed ups become a net win in practice.
So was it a surprise when Peter Shor provided that algorithm? Was that something at the time people were shooting to do, to try to go beyond applying quantum computers, at least theoretically at the time, to quantum simulation, to other things?
It was a surprise. So I was 13 years old at the time, so I don't have a direct memory of these events. But there were indications, for a year or two prior to that, that quantum computers were more powerful than classical computers for some specific structured problems in classical computer science. A lot of that came from Umesh Vazirani, who was my advisor, my PhD advisor at Berkeley later, and his a student, Ethan Bernstein, and then someone named Dan Simon. So what they did is they found artificial problems where quantum computers could get an exponential speed up. And there's a famous story that Simon wrote a paper showing this exponential speed up for this sort of artificial black box problem via a quantum computer, submitted it to the premier conference in theoretical computer science, and the paper was rejected because people thought the problem is too artificial. We don't need to hear more about this science fiction-y quantum computing model. But there was one guy on the program committee who thought the paper should have been accepted. That was Peter Shor.
Wow.
Okay. And Shor looked at this and said, well, wait a minute, if you just change this, in various ways, it seems like that would let you find the period of periodic functions. And obviously, to him at least, if you could do that, then you could also factor numbers. So he then spent a year working out the details of that. And that's what we now know as Shor's algorithm.
Which is I think many people have heard of Shor's algorithm. I don't know how many people have actually gone through it if you're not an expert in the field. I recently went through it because I thought I could come up with a nice, simple explanation for the general public of how this goes. And sure, you can talk generally speaking, but when you get into the gut of the algorithm, it is a tour de force to have been able to figure out how to do this.
Yes. Yeah, no, I mean, it is, I think, one of the great achievements of theoretical computer science as a whole. I teach it to my undergrads. It takes me about 3 lectures to do.
Yeah.
And when people ask me to summarize it in one sentence, I say, well, can I at least have 5 or 10 minutes?
Yeah, right.
But there's a half of Shor's algorithm that has nothing to do with quantum mechanics at all, right? It's just number theory.
Number theory. Yeah,
it's just reducing the problem to this finding the period of a periodic function. And then there's how do you use a quantum Fourier transform to extract the period. That's the part that really depends on quantum mechanics.
Yeah. And so that was, what was that, 25 years ago or something?
30 now.
30 now. Yeah. So in the 30 years since, one might have thought we now have this large library of other problems, that there's a quantum algorithm that would allow a quantum computer to do, that computation really quickly. What does that library look like today?
Yeah, well, so I've heard the complaint very often. Why aren't there more quantum algorithms? I call it the Rumpelstiltskin complaint, right? Like, you could spin this much straw into gold. Why not more, right? So we do know a lot more quantum algorithms than we knew 30 years ago. So famously, there's Grover's algorithm that was discovered in 1996 for searching large lists. In about the square root of the number of steps that a classical computer would need. Now, compared to Shor's algorithm, that has enormously wider range of applications, but the speed up is more modest. So that's the trade-off. And then we know dozens more quantum algorithms today, but most of them, if you look at them, they either derive somehow from Grover's algorithm or they derive somehow from Shor's algorithm. Like, they're related in some way to one of those two. So it looks like the most fundamental techniques were discovered pretty early on. And since then, people found more and more applications for them. Now, if you really want more quantum algorithms, I have a particular point of view about this, which is that I think we just need more target problems for those algorithms to solve. So part of the issue is that in theoretical computer science, problems tend to organize themselves into this small number of universality classes, right? So we have this class called P, which is all the problems that are solvable by a classical computer in polynomial time, meaning time that scales just like the size of the input or the size of the input squared, or something like that, but not exponentially. And for those problems, we can already handle them with a classical computer. So there's only a limited quantum speed up that you could hope for. And then above it, there's this infamous class of NP-complete problems, as they're called, which are these famous hard problems, many of them about combinatorial search, optimization, satisfying a whole bunch of constraints, like a Sudoku puzzle or a jigsaw puzzle, or optimizing a flight schedule, things like that. And now for those, most of us believe that quantum computers will not give you an exponential speed up, right? At least we know that if there is one, then it has to look fundamentally different from either Grover's algorithm or Shor's algorithm, right? Just like we can't even prove that there's not a fast classical algorithm for these problems. This is the famous P versus NP question.
Yeah.
But it would be a huge surprise if there were even a quantum algorithm for these problems. So then, what does that leave? Well, that leaves the problems that are sort of in the no man's land, the demilitarized zone between P and NP complete. And there are a few such problems. Factoring is one of them, right? For factoring, Shor did design an algorithm. Likewise, for various other problems in number theory that are in this demilitarized zone. Okay, but all the problems there are weird in one way or another. And so I think we need to sort of think more broadly about what kinds of things could a quantum computer help with. So, to give you an example, 6 or 7 years ago, I and others came up with a potential new application for quantum computers, which is generating cryptographically certified random bits. Right? It's very easy to use.
What exactly does that mean?
I'll tell you.
Okay.
It's easy to use quantum mechanics to generate random numbers, right? If you just put a Geiger counter next to some radioactive material, you're going to get randomness. Okay, the hard part is, what if you have to publish these random bits on the internet and everyone has to believe you that they're random? They don't trust you, right? So, for example, if we're using a proof of stake cryptocurrency, like Ethereum now is, right? It requires a huge source of randomness, and everyone has to trust it. There's billions of dollars riding on that. Okay, and so there's all sorts of ad hoc solutions to that problem, right? But they can all be gamed or attacked in various ways. And so what some of us realized is that if you have a quantum computer, you can challenge the quantum computer to solve certain kinds of problems quickly, where a quantum computer can do it, but only by sampling a random solution, a solution that has a lot of genuine entropy in it, which can then be used as a source of randomness. And even for a quantum computer to solve this problem in a way that was secretly deterministic, it would have to solve a problem that we think is hard, even for a quantum computer, right? So this, I'm not sure how useful this will be. I mean, we did patent it. We licensed it to Google for a while, but it hasn't actually been deployed for customers yet. Although it could more or less be done even with currently existing quantum computers, this sort of thing, right? Wow. But this is one example of a kind of application of quantum computers that people hadn't even been thinking about, right? Where you use, like in a cryptographic protocol, by proving that you have a quantum computer, you can also prove other things that are useful. And so I think we ought to think outside the box a little bit if we really want to, deliver like Rumpelstiltskin on the, this promise of more quantum algorithms that people keep asking for. We could also just say to people, like, be grateful that there are these incredible quantum speedups that there are for, purely classical problems. I mean, like a priori, there didn't have to be even one of them.
Yeah,
we should be grateful for that.
So was that do you have many patents of that sort, or is that like
I only have one. That's I think that in 25 years of quantum computing research, I think that's the only thing I did that had any risk of being useful.
Wow. So just taking a step back, and then I want to get to quantum computing proper.
Yeah.
Like, were you like a math kid, presumably, or a physics kid? I mean, like,
I think that would be fair to say. I mean, probably we both were.
Yeah, I think I heard that you started calculus at 11. I was 13, so
All right.
you're precocious, certainly by my standards for
Well,
sure.
my parents hired a babysitter for my brother, and she had a book that had this, D over DX in it, and I wanted to know what that meant. Just like when I had a graphing calculator, I wanted to know what are sin and cos and tan. What
Ah,
do those mean? And so then, I had to find out. It was like this secret lore, and how can you resist wanting to learn a secret?
yeah. No, I have to tell you, and I don't wanna go down this rabbit hole because it could take us the whole time, but you mentioned graphing calculator
Hmm.
as a little inspiration. For me, it was the very first Texas Instrument
Mhm.
calculator because I'm a good deal older than you. It was the SR-10,
Yeah.
which no graphing. It could just do the most basic operations imaginable, and
Yeah.
yet I still felt there was this magic in this machine
Yeah.
that I needed to understand what kinds of calculations were possible and compare it to what I could do by hand. So yes, we won't geek out completely for the whole time, but yes, I know the feeling. So then, did you ever think about going into? I mean, you may consider yourself. Do you consider yourself a physicist or computer scientist or somewhere
Computer
in between?
scientist.
Yeah. So
Computer
did
science.
you ever think about going to like physics proper? Because
I
obviously you know a
did.
huge amount of
I
physics.
I I did. I took some physics as an undergrad, and I realized that I have no intuition for partial differential equations.
Hmm.
You know, I'm so much more comfortable once everything is discrete,
Right.
and also once everything is properly defined, right?
Ah.
I want to know, what objects are we dealing with? Is this a countable set? Is this an uncountable set?
Right.
And certainly once you start getting into quantum field theory, people are very coy about that. About what are the actual objects that we're dealing with. And so I maybe I'm not proud of this, but I maybe ran away in fear and went into a theoretical computer science, which is you could consider a branch of math.
Yeah.
It's a branch that's done in computer science departments, and what I loved about it is that there are these worlds that you can fully understand because you've defined them,
Yeah.
you've created them, right? I mean, I think I got into computer science in the first place because when I was 11 or 12, I wanted to make my own video games, right? Which were
Right.
These worlds that clearly someone understood because they had built
Built
them,
it. Yeah. Yeah. Yeah.
and and once you learn what programming is, which when I found out, I mean, I was like learning where babies come from. Like, why didn't anyone tell me earlier, right? It's just incredible that that this whole problem of making a game or a simulated world can be reduced to math.
Yeah. Yeah.
But once you learn about Turing universality, how every programming language can emulate every other one, then you may come to a point of view that the details of the laws of physics, these are just some encoding details, right? These are just okay, let the physicists worry about that, but it's just the laws of physics are just yet another programming language,
Yeah.
right?
Sure.
and
For sure.
if what you care about is what can ever be computed, it doesn't even matter that much.
Yeah.
Okay, but then quantum computing comes along and challenges that somewhat. It says, no, actually, you do, if you want to know what's efficiently computable, you do need to pay attention to what the actual laws of physics in our world are.
Right.
And so that was sort of my route back into physics a little
Right.
bit.
Yeah. That's a vital
Yeah.
point. That's a vital
Yeah.
point. Now, look, I would not feel at all comfortable teaching anything to do with computer science, but I presume, would you feel comfortable teaching like quantum field theory? Does that?
Quantum field theory, no way.
Okay.
No way in hell. But I do teach the undergraduate quantum information science course at UT Austin. I've got people from computer science, from math, from electrical engineering, from physics,
Mm.
all taking that. And we have no physics prerequisite, right? Just like linear
Oh,
algebra and programming, and so what we spend the whole first month doing is just teaching the basic principles of quantum mechanics.
yeah.
and And what I love about this subject is that, you can see all the conceptual issues, and the Bell inequality and quantum teleportation, and, all the arguments for all the different interpretations of quantum mechanics, at least understand what people are arguing about, and decoherence and all these things, without ever having to see, a differential equation, without ever having to see a Hamiltonian or an infinite dimensional Hilbert space. So you cut away a lot of the mathematical complexity, which is important, of course, if you want to know, if you want to understand the hydrogen atom, for example. But if you just want this conceptual core of quantum mechanics, then, we have this more direct path. And, and then once you learn that, then, at least in my experience, you're in a far better position to learn, what is a boson? What is a fermion? What is a Hamiltonian? And then, you can actually start talking to your colleagues in the physics department. And
but you actually show them the Schrodinger equation? I imagine they must see the Schrodinger.
Not in. Well, I show them unitary evolution. We prove all the properties of unitary evolution, and then I say, well, for the physicists, they think of this as something that's continuous in time. We think of this as a sequence of discrete steps. Right. This is what I do with the Schrodinger equation. In my Quantum Information Science 2 course, we do define the Schrodinger equation and Hamiltonians and even H-bar at some point.
There you go. So, obviously we can't teach your quantum information course right here, but I would like to, in like 5 or 7 minutes, give people a sense. I've tried this in other programs. I've described it, but I'd love to sort of hear your take on it. There's this usual lore when people talk about quantum computing to say, well, in quantum mechanics, a particle can be in a superposition, a mix of, say, spinning up and spinning down, which means you've got many of these qubits. Then they can do many calculations in parallel, and that's where the speed up comes from. But people tend not to then go the final step and say, but how do you get the answer you're interested in from this morass of parallel computations, which is sort of where the heart of the issue is?
Absolutely.
So can you just help walk us through that so that we can get a feel for what the issues are and how you solve it?
With pleasure. So a qubit, as many people have heard, is a bit that can be in a superposition of the 0 state and the 1 state. Okay, but what do we mean by that, right? I mean, even in the normal classical world, right? If I have a bit and I just don't know if it's a 0 or a 1, I could describe my knowledge of that bit as a mixture of the two, right? I could say it's 70% 0 and 30% 1, and then I look at it and I find out which, and I think like when I, took chemistry in high school, for example, and they taught you, well, the electron is not really orbiting the atom like a planet. It's in this smear of probability waves. Of course, I thought to myself, like, isn't that just a fancy way of saying that, they don't know where the electron is, right? And I think the problem with the usual popular account is that it doesn't really answer that question, right? Yeah. And to answer it, you got to say something about, what quantum mechanics does is to change the rules of probability, right? And so now instead of just probabilities, which are these numbers from 0 to 1, we have these new numbers called amplitudes, which can be positive or negative, or even complex numbers.
Yeah, right.
Even complex numbers. Yeah, for almost everything in quantum computing, positive and negative real numbers would be enough. But yes, they can be complex as well. That is the choice that nature made. And so, and now the key is, if I'm interested in the probability that something happens, like that a particle reaches a certain place on a screen, I first have to add up the amplitudes for all the ways that could happen. Okay. And if some of those amplitudes are positive and some are negative, for example, then they can cancel each other out. So the total amplitude is 0. Okay. And then there's a rule for turning the amplitudes into the probabilities that I'll see one thing or another, which involves, I take the absolute value and then I square it, right? This is the famous Born rule. Okay, so but if something has an amplitude of 0, then its probability is also 0, so it never happens. Okay, so kind of the key point is that if I have an event that could happen one way with a positive amplitude and another way with a negative amplitude, these two possibilities can cancel each other out so that the event never happens at all. Whereas if I close off or block one of the paths, then I get an amplitude that's only positive or only negative, and now the event can happen. Okay, so by decreasing the number of paths that a particle could take to reach a certain place, I can increase the chance that the particle gets there. Okay, and that's kind of the smoking gun that we're dealing with, not just at some detail of particle behavior, but with a change to the laws of probability themselves. And now the next thing to say is that if I have, so a qubit is just a bit that has an amplitude to be 0 and an amplitude to be 1, right? Now, if I measure the qubit to ask it if it's 0 or 1, then I will force it to make a choice. It will snap to one or the other with probabilities dictated by this Born rule. Okay, but if I don't measure it, if I just leave it isolated, then the amplitudes evolve by their own rules, right? Which are different from the rules of probability. Okay, where the amplitudes can now cancel each other out, and I can see that later when I look. Okay, now if I have two qubits, then the rules of quantum mechanics are unequivocal. I cannot just write down amplitudes for each of the qubits separately. Okay, I need an amplitude that both of the bits are 0, so 0, 0. I need an amplitude that the first one's 0 and the second one's 1. I need an amplitude that the first one is 1 and the second one is 0, and I need an amplitude that they're both 1. So 4 amplitudes. Okay, if I have 3 qubits, now I need 8 amplitudes. Okay, for 0, 0, 0, for 0, 0, 1, and so forth. If I have 100 qubits, I need 2 to the 100 power amplitudes. Okay, if I have 1,000 qubits, that's 2 to the 1,000 amplitudes, which is more than I could write down in the entire observable universe. If I used every atom to write down another amplitude. Okay, so and we've known this for a century, right? This was right there in Schrodinger's paper in 1926. That quantum mechanics just contains this exponentiality in it. It contains this enormity that just to keep track of the state of 1,000 measly particles, nature has to maintain some scratch paper, in some place where we don't see it, with 2 to the 1,000 power parameters, or more. And every time something happens to those 1,000 particles, nature has to cross off all the numbers in its vast scratch paper and replace them by new numbers. Okay. And so, as soon as you hear that, you think, wow, that is an immense amount of work that nature is going to under the hood. Like, why shouldn't we be able to exploit that to solve problems faster? Right. But the whole difficulty is, well, for a computer to be useful to us, at some point we have to look at it. We have to measure. We have to get an output. Okay. And, with a quantum computer, it's true that I could create an equal superposition over all of the possible answers to my problem, even if there were exponentially many of them. That's even an easy thing to do with a quantum computer. Okay, so for example, all possible cryptographic keys or all possible routes for my traveling salesman or whatever. I could put them all in superposition, all with equal amplitudes. Mm-hmm. But now if I just measure that, not having done anything else, then quantum mechanics tells me that all I'm going to see will be a random solution. And well, if I just wanted a random solution, I didn't need a quantum computer. I could have just flipped a coin a bunch of times, right? Saved myself billions of dollars. Okay, so the only hope of getting a speed up from a quantum computer is to exploit the way that these amplitudes work differently from probabilities. Okay, and the name of the game with every quantum algorithm is to try to choreograph a pattern of interference so that for each wrong answer, each answer I don't want to see, some of the contributions to its amplitude are positive and others are negative. So they're canceling each other out. They're interfering destructively. Whereas for the right answer, the answer I want to see, I want the contributions to its amplitude to be pointing the same way, to be in phase with each other.
Yep.
Now, if I can arrange that, then when I look, I'm going to see the right answer with a high probability. And of course, I can keep repeating the computation until I see it. But the tricky part is I have to choreograph all of this, even though I myself don't know in advance which answer is the right one. If I already knew, what would be the point,
Yep.
right? And I have to do it faster than even the cleverest classical algorithm could do the same thing. Because why build a quantum computer if it's not going to beat a classical computer? Okay, so nature is giving us this really bizarre new interference power, and a priori it's not really obvious that it helps for much of anything other than maybe simulating quantum mechanics itself, right? You still have to be clever. This is not like a magic try all answers in parallel genie, because you still have to choreograph this interference pattern to collect the amplitude on the answer that you want to see.
So that's the key. That's the key point. So thank you. That was wonderful.
Thanks.
And so just to bring it back to the example that we started with Peter Shor. So the genius of that algorithm was finding the choreography.
Yes,
that
precisely.
would cancel out anything but the factors of whatever composite number you're seeking to factor.
Precisely.
And so in the midst of that conversation, though, you mentioned you nicely anthropomorphized an electron or something. You say, when we look at it, we force it to decide. Right?
Yes.
So that's the famous quantum measurement problem.
Yes.
And just where do you stand? My view is that is a big missing piece in our understanding of quantum mechanics. There are others who are like, oh, stop. You're just looking for too much. It's the old shut up and calculate. Just use quantum mechanics to get a result. So where do you stand on the issue of how does a measurement coax a particle to ante up to one of the many possible outcomes that could happen?
Yeah. Well, I've worried about this my entire life, at least since learning what quantum mechanics was, right? In grad school, I, went down a rabbit hole for like a year. I thought, maybe I will, use insights from quantum computing to solve the measurement problem. I gave up on that, I should say. But I think, the hard thing about the measurement problem is that, we can tell a very compelling story about, what happens during a measurement, that, a quantum system, was, in a superposition, and then, it leaks its information into its environment, into the outside world. So, for example, I have a qubit that's in a superposition of 0 and 1, that, and now we look at it, that just means we apply some physical process where now the state of a much larger system, like our measuring device, our photo detector, eventually even our eyes, our brains, the air in the room, will all be in a different state depending on whether that qubit was 0 or whether it was 1. Okay, and now if we just follow the equations of quantum mechanics, they are perfectly happy with all of this, right? What they want to say, in a sense, is just that, our whole system, our measuring device, our bodies, the room, are becoming entangled with the qubit, right? And now we have one branch, we have some amplitude that the qubit is 0, and all this other stuff, including our own brains, has registered as 0. And then we have another branch where the qubit is 1, and all this other stuff has registered a 1. Okay, and this picture all works very nicely, except for the one obvious question that it leaves unanswered, which is, well, then why do we experience only one and not the other, right? The many worlders would say, well, just because we happen to be in one branch and in the other branch, there are there are doppelgangers of us who also have a perfectly valid experience, and they experience the other outcome, right? The Bohmians would say, well, there must be some hidden variables that determine that only one of the outcomes is actually experienced, even though they agree that both of them remain there in the equations, right? And then the Copenhagenists would say, shut up and stop asking, except they would say that in a lot more words, right?
And where do you come down?
I feel like we're missing something. We're probably missing some crucial insight.
there are also people who say that none of these answers are satisfactory, and the only possible solution is that quantum mechanics must be just an approximation to some better theory. So, Roger Penrose, for example,
or Tufte, people like
yeah, that's right. That's right. And so I say, okay, then let's see the experimental evidence. And I say, why do you think we're trying to build a quantum computer? Well, for me, one of the big reasons is to test quantum mechanics as severely as we can.
Right.
Let's put it to the test. I welcome that confrontation with experiments, right? Let's see, does quantum mechanics continue to hold at the macro scale, or at as large of a scale as we can test it.
Yeah.
So I am partial to the idea that cosmology might play a role here. That's been advocated by Lenny Susskind and Raphael Busso, for example. If we want to say that like only one outcome is experienced, or that sort of measurement is a real thing in the universe, the hard part has always been to say, well, when exactly does the measurement happen, right? Because it seems like if you just follow the Schrodinger equation, that at any point, you could still reverse things, right? You could still, there's no definite point where the buck stops and the measurement has happened. But once you bring in cosmology, then you could say, well, at some point, the information about whether that qubit was a 0 or a 1 is now entangled with photons that are escaping the Earth, that are flying away from us at the speed of light, heading towards our cosmological horizon, of our de Sitter boundary or whatever. And even in principle, those can never be collected again. They could have been if some aliens have surrounded the solar system with mirrors,
Sure.
but I take it that they haven't, right? And so we could say, maybe cosmology provides the ultimate criterion for when a measurement has sort of irreversibly happened, and maybe that's part of the story.
Right.
So I am not, I would say, a hardcore many worlder, because I am open to ideas like that. But then also when people use really, really bad arguments against many worlds, then I tend to get angered and provoked about that.
Yeah.
and I tend to want to rush to the defense of many worlds, because
it's funny because I have a similar reaction, and was surprised that you mentioned, but pleased that you mentioned the Bohmian approach, because not many people take that at all seriously. And the usual argument that people make is, well, it's got non-locality. I really emphasize that is the real dominant. I should have said non-locality. And what always troubles me about the non-locality argument is that, well, ordinary quantum mechanics has non-locality, and it's just not in your face. Right?
Bohmian mechanics definitely makes it more in your face. Right. You still, it's still empirically the same theory as standard quantum mechanics. You still can't actually use it to send a signal faster than light. But, Bohmian mechanics really rubs your face in the non-locality. The Bohmians would say that's good. If it's going to be there, then you might as well be confronted with it. And look, there have been some brilliant, Bohmians. John Bell was, a huge fan of Bohmian mechanics and was led by it to discover his famous Bell inequalities, right? But my problem with Bohmian mechanics has always been something different. It's been the sort of radical non-uniqueness of the rule that governs the hidden variables, right? So the issue is, Bohm wrote down one particular rule for, the evolution of the hidden variables that he posited, that would match the predictions of standard quantum mechanics. And, if you just have one particle moving around in a potential, for example, with no spin or anything like that, then, this rule has a reasonably unique character to it. Right? But as soon as we start talking about discrete systems like spin, we start talking about different kinds of quantum systems with different Hilbert spaces, then, I could write down a million different rules that all have the same property of Bohmian mechanics, that they're going to reproduce the Born rule, right? And so these are all narratives that I could tell that are all empirically indistinguishable from each other, right? And I have trouble knowing what it even means to say that one of them is true and all the others are false.
Right. But to balance that,
Yeah.
though, isn't it impressive that whereas in standard quantum mechanics, there's so much you have to give up from classical physics. You have to give up, positions, velocity, simultaneous trajectories. You have to give up all of the things that we hold dear in classical physics. And then you go to Bohmian mechanics, and yeah, you got to give up some things, but you can preserve the idea of the basic reality composed of trajectories of particles.
Yeah, well, I would argue. I mean, of course, that's the central selling point of Bohmian mechanics. Since the beginning, since Bohm, or even before him, De Broglie, I guess, right?
Yeah.
But I would say that to some extent that's illusory, right? Because if you think about something like a quantum computer running Shor's algorithm, right? Like, it is clear that what is doing the actual work is this exponentially large wave function. Right, it's this vector of amplitudes, and the hidden variables are just sort of bobbing around in that vector of amplitudes. It's kind of like a little plank of wood, in an ocean, right, or almost comically irrelevant to the real action that's going on, right? And then also the whole intuition that we can have particles with real positions in three-dimensional space. Of course, this is just for non-relativistic quantum mechanics, right? Because once we go to quantum field theory, then the nature of the hidden variables is going to have to become something else, something much more abstract, to say nothing of quantum gravity. So I think, once we start incorporating, everything we know about physics, we're going to give up on the simplicity and elegance that were some of the main original selling points of Bohmian mechanics.
Yeah, for sure. I absolutely agree with that completely. So let's just turn back, if we would, to quantum computing a little bit more detail. So where would you say that we stand in realizing these potentialities in terms of, I guess, a scalable quantum computer? There are various architectures, approaches. I'm not an expert on it, but superconducting circuits, trapped ions. Where would you put your money on? Which one is going to succeed? Will they all succeed in different ways? Where do you think we are?
So if I had great skill in prognosticating, I wouldn't be a professor. I would be an investor, and I'd have a much bigger house, right? But I think if you look at where the experimentalists are now compared to where they were when they started 25 or 30 years ago, the progress has been absolutely staggering. Okay. Now it's true that we don't yet have a scalable, error-corrected, programmable quantum computer that can run Shor's algorithm to factor, 2,000-digit numbers. Okay. We don't have that yet. But a lot of what the skeptics said, were sort of the essential prerequisites to that would never be done. They now have been done. Okay. Some of them within just the last year or two. Okay. So I think, the most important number to look at if you care about experiments is called the 2-qubit gate fidelity. Okay. So it's like, how accurately can you apply an operation that would entangle 2 qubits, right? Or do a unitary operation on 2 qubits. When I started in this field, which was in the late 1990s, it would have been like a Science or Nature paper if you could do a 2-qubit gate that was 50% accurate, right? Meaning, like maybe there's a 50% chance that the gate fails, that it leaks the information into its environment, that it decoheres, that the angle of the rotation is off, and so forth. Okay, but at some point that 50% became 90%. The 90 became 99%. Now, within the last year, we have seen groups in superconducting qubits, in trapped ions, and in neutral atoms, all at or approaching 99.9% accuracy.
And what do you need to get to be
Excellent question. So now, the skeptics of quantum computing back in the 90s, they said, well, you're never going to do this because you'll just have to improve your reliability arbitrarily, right? And you're never going to get gates that are perfect. But a key discovery that was made 30 years ago shortly after Shor's algorithm, actually, was called the theory of quantum error correction. And what that ended up telling us is that you don't need perfect operations. You only need operations that are very, very good, right? And you just have to get the rate of error below some constant. And after that point, there are these very clever quantum error correcting codes that can get you the rest of the way. Okay, so basically you encode the information you care about, the logical qubits, they're called, in entangled states of many, many physical qubits in such a way that even if a few physical qubits, fail or leak into their environment, you can still recover everything you need from the other qubits. And so you're constantly monitoring your system, you're constantly measuring, but only to see where has an error occurred and what do I have to do to fix it. Not to see, is my logical qubit a 0 or a 1, which of course you don't want to know. If you learn that, it would destroy your
game over at that point.
Right.
Yeah.
And so the original estimate, I think, in the 90s was that, this whole scheme will start working. That is, it will give you a net gain. It will correct more error than it is causing. Once you can get physical 2-qubit gates that are like 99.9999% accurate, right? And people said, yeah, fat chance, you're ever going to get that. Okay, but theorists said, okay, this is good. It's just a constant, And since then, people have improved the error correction schemes, and now we think that it should scale once you have just 2-qubit operations that are merely 99.99% accurate. Okay.
Right now we're at 99.9.
And now we're at about 99.9. So we're about 1 9 away from what, on paper is, is sort of the critical mass, if you like, right? The sort of the critical threshold where once you pass it, then, it ought to be merely an engineering problem of, now maybe, it will cost billions of dollars. You'll have to, fill an entire building with dilution refrigerators with, different chips that are communicating with each other and that will have millions of physical qubits. But, in principle, it should work. So I think that, if you compare to like, getting a nuclear chain reaction, for example, we're now like at least at 1939, I would say. And so, so I would say, based on what's happened in the last year, I would say, either we're going to see something really impressive in the next decade, towards scalable fault tolerance, or else something unexpected is going to happen that's going to block that.
You're saying it could be 5 to 10 years or never. I mean,
look, there could be some unexpected difficulty that makes it take 20 years. I mean, like I said, I'm not, I don't have such a great record of prognosticating how many years things will take that people should trust me. I'm just a theorist, right? But if you just look at the 2-qubit gate fidelities, I mean, and you just plot on a graph, like when is that going to cross the fault tolerance threshold? You get estimates that are well within the next decade.
Yeah,
so that's what I can say. Now, there's all kinds of uncertainty. We have an election in the U.S. in a month. I hope that civilization will last. Beyond that, I hope that AI won't become super intelligent and destroy the world before then. Right? There's all kinds of uncertainties about the world as a whole. But, if quantum computing continues along its current course, I think everything that we've seen so far, suggests that, first of all, this is an engineering problem. It's not a problem of fundamental physics. And second of all, we've now seen that, whether or not it's a wise investment or an unwise investment, companies are making the investment. Right. That means Google, Microsoft, IBM, Amazon, a whole slew of venture-backed startups, a bunch of governments, the US, the EU, China. They're now pouring billions of dollars into this. So, it's still small compared to, let's say, the investment in AI. Okay. But, by the standards of academic research, it's quite big.
So I want to turn to AI in a second, but I just want to
Yeah.
double check. So you said all three of the technologies
Oh,
that you mentioned, so the trapped ion, the
yeah.
superconducting, and the neutral atom, all of them are at the same
Well, yeah, I
99.9?
would say that right now, maybe trapped ions and neutral atoms are the furthest along in terms of what has really been demonstrated with fidelities. Superconducting is at worst only slightly behind,
I see.
right? But 5 years ago, I would have said that superconducting was the furthest
I see.
along. Okay,
I see.
and it's tough because if you talk to the people working on any one of these approaches, they will spend hours bad mouthing all the other approaches, right? And telling you why the other approaches, it's going to be super duper hard to scale them, right? And so, I can only look at, I'm not an experimentalist. We once had a funder said, can I visit your lab, Scott, at UT Austin? Can I see your dilution refrigerator? And I said, you realize we're theorists. We have a fridge for leftovers. Okay. But, all I can do is talk to the experimentalists. I can see what they've actually done so far. And, and all the approaches have done, I would say almost, comparably impressive things at this point in scaling. They all have, a lot of engineering difficulties going further. Another approach is photonics, using photons as your qubits. There's also something called quantum dots. So, there's topological qubits, which Microsoft has made a huge investment in, which might ultimately be the best way, but it requires creating a new state of matter that's never been seen in nature.
Yeah.
So it is possible that just like the Manhattan Project did both a uranium bomb and a plutonium bomb, right? And in the end, both designs worked.
Yeah.
Right? Yeah. They're
I'm not sure I love that analogy, but yes, it makes a lot of sense.
It is one that people keep bringing up for better or worse. But
well, going with that analogy.
There could be just multiple approaches that work,
totally.
and it'll be a question of economics of
right. But going with the analogy, going with the analogy for a second. So if it could be that scalable, fault tolerant quantum computer, let's say it is 5, 10, whatever, some our lifetime, or God willing, our lifetime kind of thing. Would you advise, maybe you have the U.S. government to plan for the possibility that all of our cryptographic encoding of sensitive information we should switch to an approach that is more resilient to a quantum computational attack?
So yes, I would advise them that. The good news is that as dysfunctional as our government is in many ways, they are at least there are parts of the government that are well aware of this and that are already trying to be on top of this. So NIST, which is the National Institute of Standards and Technology, had a competition starting in 2017 to come up with standards for what we call post-quantum or quantum-resistant encryption. And to be clear, this is just encryption that runs on ordinary classical computers. Right? There's also quantum cryptography, but that's a different approach. This is just classical cryptography, but that is based on different hard problems than the factoring problem. Right? It's based on different principles, and at least so far, it's cryptography that seems to resist attack even by quantum computers. Okay, we have no proof of that, but there's hardly ever an unconditional proof that anything is secure.
Yeah, I looked at one of them with lattices and trying to find
exactly.
Yeah.
So that so NIST sort of converged, I would say, in this competition on what are called lattice-based crypto systems, where the encoding is done by sort of applying a linear transformation in some very high-dimensional lattice and then adding a small amount of random noise to the result, right? And the key is that if you just have this and the lattice, but you're told it in sort of a bad way via a bad basis, then the random noise makes it impossible or makes it totally infeasible for you to decode. what that message was. Whereas if you have a good basis for the same lattice, then you can overcome that noise and you can decode the message. So that's the basic principle of these crypto systems. They've been around for about 30 years now, which means that they're not all that much younger even than RSA, and the systems that we use, which are, let's say, 50 years old, right? And and people have been trying to design quantum algorithms that would break these lattice systems, but they haven't succeeded yet, right? And so that's about the best that we could say. A bunch of attempts by very smart people to break these things, either quantumly or classically, have failed. And I think 10 or 20 years ago, the word about these systems was, sure, they're quantum resistant in principle, but they're just totally impractical. They require, for example, enormous keys or enormous messages, and they're just going to be too slow in practice. I think that today these systems have been improved to the point where they are pretty practical. Okay, and there are even people who are using them today. Unfortunately, to get everyone in the world to upgrade their web browser or their server or their router to use quantum resistant cryptography, that's going to be a big headache.
Yeah.
I mean, for God's sakes, there are people still using Windows machines that were compromised in the 90s. Right. And so, but that's a big practical problem. But, once everyone does that, then, you could say, hopefully, if all goes well, we'll just all be back where we started, so we can enjoy the benefit of quantum computers for quantum simulation, for, discovering new materials or new drugs potentially, and not have it break the internet. Right. But I would, given what's happened in experimental quantum computing in the last year or two, I would definitely advise people who are paranoid, who are worried about their security, think about this. Have a plan.
So jumping from that doomsday scenario to the other
it's not a doomsday
scenario. So, were you surprised in November of 22 with Chat GPT, or was that something that you were sort of watching it progress?
Well, I wasn't surprised, but the only reason why I wasn't is that at that point I was already working at OpenAI. And I had accepted their offer in the spring of 2022 to join them and start, thinking about what can theoretical computer science do for AI safety. So Ilya Sutskever, who was at that time the chief scientist at OpenAI and their co-founder, and Jan Leike, who was the head of AI alignment there, approached me, and said, "Why don't you take a year's leave from quantum computing and help us think about AI safety?" And I was very skeptical. I said, "Why do you want me? I'm a quantum computing person. You're not doing quantum computing, and also you're in San Francisco, and my family is in Texas." And they said, "No, we read your blog," they said, and we think that there really are theoretical questions, and this is AI is getting to the point where it's going to change everything, and we need people thinking about how to make it safe. And now, at that time, I had played around with GPT-3, right, mm-hmm. which I had seen in 2021, and I was blown away by it, to be honest. In fact, it was maybe even the biggest empirical surprise of my lifetime.
So, really?
Right, that you would just take a neural net, you would train it on all the text on the internet, just keep training it to predict the next word, as well as possible. And throw enough computing power at this, and at some point this would go from not working to suddenly working.
Yeah.
Right? As in, it answers you intelligibly. Not like a genius. It still makes mistakes. It gets things wrong. But even the kinds of mistakes it makes are like the mistakes that a human would make very often. Right. Yeah. And you could say it for the first time, you now have a computer that you can talk to in English, and that could, if you didn't know it was a computer, you would say it understands something, right?
And if you're a
So
Turing, you might even go further than that, right?
that's right. Indeed, you might. And so and I think a lot of my colleagues, 3 years ago and even today, we're kind of in denial about this, right? Because there was such a strong prior that this couldn't work, right? This is like such a dumb approach to, you're just going to feed in all this data and train a neural network, right? Like solving AI there must be more to it than that.
Yeah, I mean, that's such an
Right?
old idea that
Yes,
never worked.
yes, that's
Yeah.
right, that's right. And we had a long experience with this not working, right? And that it would just be a question of scale, of just having a big enough computer and feeding enough data in, right? People had such a strong prior against it. And to be fair, I did not foresee this, right? I mean, I knew that it was a logical possibility. I debated the AI doom people, back in 2007, 2008, right? Such as Eliezer Yudkowsky, right? I've known him for a long time. And, and they were saying, look, we have to worry about, AI becoming, getting human-like intelligence in the next few decades. And this is even the biggest problem facing the world. Everything else is peanuts by comparison. And, that seemed silly to me. Okay. It seemed like, don't we have more pressing problems, right? Like we should only be so lucky that, worrying about the Terminator taking over, would be our biggest problem. Right. And I said, look, in principle, I agree that this all could happen, but who knows how long it could be? I said, it could be thousands of years for all we know, until we, unravel the secrets of intelligence that evolution took millions of years, to put into us. Okay. But now, here we are, a decade or two later. And I think that, these people were onto something.
Yeah.
And I think, if I failed to foresee it, then the least that I can do is update.
Yeah.
And so yes, I was deeply surprised to see GPT-3. That's when I had my, my holy hell moment, did my big update. And then once I joined OpenAI, then I, even before ChatGPT was released, that I saw GPT-4 internally, got to use it. And so I was in the very unusual for me position of not being allowed to talk about it, which was frustrating, right? Because I'd see people on social media like ridiculing GPT-3 that, it makes all these common sense errors. And I could try the same prompts in GPT-4 and I could see that it knocked them out of the park.
Yeah.
I wasn't allowed to say. Right. But the release of ChatGPT in November 2022, OpenAI didn't expect that was going to catch fire the way it did. They intended that as just a little teaser for GPT-4. Okay. But as soon as they just made a nice interface where anyone in the world could use this, like that was really the key. Yeah. That was the spark where sort of everyone suddenly woke up to what had now become possible, what the experts had already known for a year or two at that point was now possible.
And do you see the increase in capacity of these large language models to just continue on the current curve? Or do you imagine that we'll run out of data, or they'll run out of steam, or they'll just hit some ceiling and we'll have to do something else to go the next step?
Yeah, well, that's a huge question, isn't it? I mean, given that we had no theoretical principle for predicting, the success that the LLMs have already had, right? It was all just sort of guesswork and, staring at graphs and empiricism. Right. Far less do we have a principle to predict, where things are going next.
Yeah.
So, there's this saying that like every exponential in the real world is actually a sigmoid in disguise. Right. Like every, like super rapid transition is going to peter out eventually. Right. And in this case, we can sort of see, what will happen. I mean, there is only so much training data, on Earth to be fed in. Right. And like most of the text and the public internet is already being exploited, to the extent that there's all sorts of lawsuits over copyright violations. Yeah. Right. And, it's true that all the content on TikTok and Instagram and so forth, hasn't been fully exploited yet.
Will that
But
make it
like you
better or
say,
worse,
that
though?
might, yeah, exactly. That might just make the AI stupider rather
Yeah.
than smarter, right? So you could hit diminishing returns here, right? There's also a problem with compute. I mean, Microsoft just literally bought the rights to all the power from 3 Mile Island, which they're going to restart. Right?
Really?
Did you see this?
I
Yes.
did not
So
see that.
yeah. So the Microsoft and other tech companies are now investing in building their own nuclear plants.
Oh, my God.
Okay, they want to revive nuclear power, which I think is great.
I think it's a good thing, too,
right?
if you do it
But
right.
they,
Yeah.
they mostly want it just to power data centers.
Wow.
Because they think, right now electricity is not the bottleneck, but if you just look at the trend lines, it's
It
going
will
to
be.
become the bottleneck
Yeah.
soon. And and then the total number of GPUs that the world can manufacture is another bottleneck. If China were to invade Taiwan, that would
That would be that. Yeah.
that would get much worse. But the U.S. is now investing billions of dollars in building our own fabs in the U.S. So there are these you will eventually run into both these physical limits, these limits on data, and so so let's grant that this like the improvements in performance of LLMs will hit diminishing returns at some point. That still doesn't answer the question, well, does it do that before or after they become smarter than us or smarter than Ed Witten, let's say, at pretty much everything, right? It doesn't answer that question.
Right.
Okay. And that's the very scary part.
Or better than Shakespeare, or better
Yes.
than Beethoven, or
For example. Yes.
Yeah.
For example.
Right.
And one thing that we've already seen is that even when the LLMs do hit limits, one can then construct scaffolding around them. One can use them as a component in a larger system that can do things that the LLM itself could not. So, just in the last month, OpenAI released what was called the O1 model, right?
Yeah.
Which was like GPT-4, but with reinforcement learning for multi-step reasoning, right? Where in that multi-step reasoning, it might make a lot of mistakes, but it notices when it makes mistakes and it backtracks. And then it doesn't actually show you all of its scratch work, right?
Yeah.
It just shows you kind of the final answer and a summary of its reasoning. And so then it can look really smart. I mean, it is getting performance on math Olympiad problems in line with like the top few hundred high school students in the US. Okay.
Yeah.
That's.
Now, I saw the change myself early on. I gave it, as many of us no doubt did, some general relativity problem that I give to a graduate student. The early versions, the reasoning was correct, but the math was wrong.
Yes.
And then these ones, the reasoning's right, the math is right, and it's just, completely right.
Yeah. So I mean, once you have language models that are really tightly integrated with, let's say, an automated theorem proving system, right, where it can just, check, formally verify the correctness of every, a step of reasoning before it shows it to you, right? Then, it is very hard to see, like, why will we say, mathematicians, physicists, theoretical computer scientists not be using this to write our papers?
Yeah. And so that is the question I just wanted to briefly turn to, the existential one. What is the role that imagine, maybe not even physics per se or computer science to take it outside of our domains, but what if the system really is the best composer, better than Beethoven, or the best playwright, better than Shakespeare? What do I even mean when I say that? First of all,
I think that's an excellent question.
Yeah.
What do we mean by that? And then you can also say, how much will we care?
Yeah.
Right?
Let me just tell you where I come on this and get your take on it.
Yeah, please.
When we listen to Beethoven or watch, Hamlet, part of the experience is the experience. Part of it is knowing that there was like this human being that had a life sort of like ours or something different that we know about. And it's the process that yields the work that informs the experience to some extent. And clearly, if we know that this is created by, chat, it just won't grab us the same way, no matter how good it is, I think. But maybe I'm wrong.
Yeah. I think that might very well be a true statement about how humans react to these things, right? We're already seeing that with AI-generated art. right? Where like, your first reaction is like, this is beautiful, this is amazing. But then there's just so much of the stuff,
Yeah.
right? Just filling your Facebook feed, filling the internet. And then, after a while, you sort of lose interest, right?
Yeah.
You just adjust, so this is related to the fact that, like when we read Hamlet or we read Macbeth or watch them perform, right? We have this consciousness that Shakespeare gave us these 37 plays, and these are the only ones we're ever going to get from him, right?
Yeah.
He's gone now, right? This is what he gave us. Whereas, if an AI generated a play, even if it was just as good as Hamlet, like you would know that there's 10,000 more where that came from, right? It can keep generating more and more from the same probability distribution. Just have to keep hitting refresh, in your chat GPT window. Okay. And so that sort of limits how much you would ever care about any one of the plays.
However, I just wonder, along the same lines, some would say, of course, well, now that system can create one just for you.
Yes.
Based on knowledge of your history and things that have fired you up or personal experiences in your own life.
Yeah.
So maybe art then becomes a singular thing as opposed to the communal experience.
Yeah, no, I mean, I think, these will have massive effects on the world. Of course, there's a question of what do people want? Do they want a play that is personalized to them, or a novel or a song or whatever? Or do they want to be sharing in this communal experience that everyone else is experiencing the same work that they are, and they can talk to their friends about it?
Yeah.
Right. So,
I think that's the big question. But now if we take it back to our field, where there's less nuance, like when I look at a theorem that's proven, I don't care if it's Gauss or a result of Ed Whitman. In the end of the day, it's the result, and how we got there is interesting in the history of science sense, but it doesn't really deeply matter from the progress of understanding reality. Like if these systems can start to generate the theorems and generate the new theories that quantum gravity, it resolves all the issues. Where do we fit into that story?
Yeah, well, I the more I play with things like the O1 model, the more grateful I am that I have tenure. But I mean, look, there are many possibilities. One possibility is that, deciding which theorems are interesting or which questions would be interesting to investigate, that will remain as a domain of human supremacy, or at least where we mostly care, about the questions that humans ask for a while longer. But that proving the theorems, we will increasingly rely on these systems to do that for us, or doing the actual calculations, to answer the questions that we pose.
Right.
And it's a hard question, even like of all the technical skills that we try to teach to our students, how many of them are still going to be relevant, right? Because on the one hand, these systems can do them. On the other hand, part of me feels like, as long as there is anything that the system still can't do, that you still need a human for, right? Then you also need a human to know all of the nitty gritty below that, right? Like,
for now,
like how could you be thinking about quantum field theory if you've never learned to do arithmetic, right?
Right.
And and of course, elementary schools have already faced that problem a long time ago. I mean, most of what my kids learn is stuff that computers have been able to do for a long time: arithmetic, spelling, hand, these are a reading, right?
Yeah, I mean, obviously, there's value to having a solid foundation in education, but then there really is nuance in what role these systems should play. And I know there's a lot of discussion in the academic community. I mean, my approach is, if you tell students you can't use them, it's not going to matter. They're going to use these systems anyway. And moreover, in the real world, those who are become expert at using these systems are the ones that are going to actually succeed. So I think we should integrate these things into the educational process from the get-go and really find a way that the student doesn't just put in a prompt and turn it in, but rather engages with the system and shapes the system in a way that most other people won't be able to, because they don't have that kind of practice or experience.
Yeah, I think that's broadly right. Now, you could say that students who were connected enough or who had enough money have always been able to cheat, have always been able to just get someone else to do the work for them. This a GPT sort of democratizes cheating in a way, right? It gives, everyone this sort of, hyper intelligent, always available friend.
Right.
But there are always simple expedients like the in-person exam, if you really need that. One of the things that I worked on at OpenAI was a system for watermarking the outputs of GPT to make it easier to detect what came from GPT and what didn't. That still hasn't been deployed. I'm hopeful that might get deployed in the future. Okay, but
students will love you for that, right? They're gonna.
Yeah, right. Well, maybe the honest students will love me, right?
Yeah, true.
That they're no longer at a disadvantage. But
Right.
definitely my fellow faculty would love me if that got deployed. But of course, no watermarking scheme that we can design is going to be perfect. There will always be workarounds for anything like this. And you could say, ultimately, we have to adapt, the way that we teach and that we learn to the existence of these tools. And, as long as the tools are still limited, as long as there's stuff that you still need us for, then it feels a lot like any previous tool, like the calculator, like, the slide, right? We can adapt to it. We can, change our emphasis in what we teach and learn, and we move forward. The scary part, of course, is, once we reach the possible point in the future when we're not really needed for anything.
Yeah, but I was going to ask about that. What happens to the, people speak of when AIs can create better AIs, self-improvement. I mean, is that something that you see on the horizon, and what does that do?
Well, that's a big question. So, John von Neumann or I.J. Good were already talking about this in the 50s and 60s, or, just like, quantum computers, reach this fault tolerance threshold when they can correct more, errors that are being introduced. AI could eventually reach this threshold where it's smart enough to design a better AI.
Yeah.
Which is in turn smart enough to design a better one, and so forth. And so, there's a whole community of, AI doomers, or, whatever you want to call them, centered around Eliezer Yudkowsky, right, who have been saying for decades that basically, this is not just science fiction. We should think about this in reality. And that once AI reaches that point of, recursive self-improvement, we should expect that unless we've taken very, very exquisite care to prevent it, the AI will probably have some goal that differs from what we would want, and it will pursue that goal. And we will fare about as well in the AI's world as orangutans fare today in a human world. Right? Like, imagine orangutans somehow, creating the first human to help them and say, okay, but it's okay because we're going to keep this thing aligned forever with orangutan values. Right? Like, what do you even mean by that? How would you do that? Right? And so, and especially if that human can transmit culture and learning to the next humans and make the next human smarter and the next one smarter and so on, as humans have been doing for the last few thousand years. So, so I think that, these now seem less and less science fictional, these possibilities. They seem more and more like things that we should worry about. I am not in the camp that says, for sure we're all doomed, right? For sure that this happens. I mean, maybe it all goes much better than we expect. One thing that we've learned from LLMs is that so far, you can literally just instruct them in English. Just give them a prompt that tells them, like, don't say stuff that's racist, right? And they will do their best to follow that prompt, sometimes even to absurd extremes, as we saw with Google's Gemini, for example. Okay. But they will do their best to follow instructions. You can also do what's called reinforcement learning, where you sort of give them a mild electric shock when they output something that you don't like. And in that way, you sort of beat them into shape. And, and these techniques have worked better than most people have expected they would. Now, the doomers will say, well, not all of that is just lulling you into false complacency. right? Because once it gets smart enough, then it will be smart enough to tell the humans whatever they want to hear, while it secretly pursues its own goal that might be at variance with our interests. So I don't know. I have massive error bars over the future. But, one thing that this definitely leads me to believe is that, yes, we ought to be approaching this with humility for the magnitude of what is being created. We ought to be trying to preserve as much optionality as we can, the ability to shut things down, to pause, if things get too out of hand, if they start going wrong. So, I am in favor of legislation to try to put guardrails on this, to sort of require disclosure of what is happening, to protect whistleblowers within AI companies, to require safety plans. I was a supporter of this SB 1047 bill in California, which unfortunately Governor Newsom just vetoed this week. I thought that was a mistake. I hope that there will be federal legislation, either in the US or in the EU, to try to put some guardrails here, right? And that doesn't require sort of any confidence in the doom scenario, right? That just requires realizing how large the error bars now are, right? Realizing the magnitude of our uncertainty about this. And
so I gather the tech community, doesn't want to spoil or restrain innovation. But do you worry, and maybe because you need 3 Mile Island power sources, just some rogue actor who's able to, the guardrails are keeping the good guys in place, but then, the rogue frees them up in some sense because the competition won't be as severe.
That is certainly a worry. Then there are people who agree about the sort of massive effect that AI is going to have on the world. They agree that it will be at least as great as the effect of nuclear weapons, or maybe even fire or writing, or if you go back far enough to something like that. Okay, but they say, well, then all the more reason why the democratic world, or the Western world, has to race to get this before the axis of China and Russia and Iran and North Korea get it first. So that's a position that you can take. My former colleague at OpenAI, Leopold Aschenbrenner, wrote a whole book about this recently, advocating that point of view. His book was just approvingly tweeted by Ivanka Trump, who apparently showed parts of it to her father. So these ideas are certainly out there in the discourse. I would certainly say that I would like for the U.S. and other more or less democratic countries to retain an edge in AI over China, Russia, Iran. No question about that. Fortunately, right now we have a very large edge.
Yes.
And even in China, for example, there are lots of people who are very concerned about AI safety. Like, my colleague Andy Yao, who is a theoretical computer scientist and now at Tsinghua University, and who very much has the ear of the Chinese government, right? He has been a very strong voice for AI safety. And so I think, we have to balance these concerns. If we see that, some government with tyrannical aims is racing to create AI that it can use for those aims, then we might face a moment, like Einstein and Szilard, felt that they were in 1939, when they wrote that letter to President Roosevelt saying, we have to build this bomb, we have to do it first. But let's proceed with caution, as of course the nuclear physicists in the 1930s wanted to proceed with caution. Let's proceed. I am not someone who advocates shutting down progress in AI. And, this bill that was just vetoed, it would not by any means have shut down progress, right? It was actually a very, very minimal bill, just with some very minimal, you have to disclose to the government, what's your safety plan? You have to protect whistleblowers, right? Some very minimal stuff. And so I think people sort of overreacted. They just didn't want to acknowledge the principle that there could be any dangers here, because they felt like once you give the safety people an inch, they'll take a mile, right? But the actual contents of the bill were very, very mild, and I think would not have compromised America's competitive edge.
So if we think about alternatives to like a doomsday scenario where AIs just take over, or we're so irrelevant that they don't even know we're there while they stomp us with unwittingly, taking up all the resources or something. Can you imagine a collaboration that would go beyond, say, us just using these systems, but maybe like, do we incorporate these systems into our physical being in some like cyborg way? Is that a possible future you can imagine?
You can certainly imagine it. I mean, in fact, almost any possibility, right? Science fiction writers have already been all over it, right? And have imagined it. The trouble is just we don't know which science fiction story we're living in yet.
Yeah.
So, but I mean, if we were to sort of gradually merge with AIs, for example, if we could all just get a chip implanted in our brain that boosts our intelligence, our memory, but we still have this sort of frail analog biological component as well, right? That would seem like a more gradual transition. Maybe we would be more comfortable with that, right? I think a lot of what makes people feel uncomfortable is the idea that we are suddenly going to be replaced by something that is not us, that it's going to be a discontinuous change. Right. But if you think about like our children are not exactly the same as us, and as any of us with children know, they even have somewhat different values, different interests. Right. And then, their children will have different values from them and so on. And, if you think about how much we have in common with our ancestors 3,000 years ago, well, maybe a little bit, but, the gap in even the most basic values is immense. Right. But we still feel like, it's not that our ancestors 3,000 years ago would feel that some other species has replaced them, because they can still see how from generation to generation there was a gradual change. Right. And so maybe, if we are to evolve into some new, silicon based or AI or hybrid cyborg being, right? You might say as long as the transition is relatively gradual, so that we can each generation can feel continuity with the generation after it, then maybe we would feel better about that. I don't know. Now,
I mean, presumably, as long as there's a sense of conscious self-awareness that persists through this melding. But I guess the worry would be, what if you create these cyborgs that are incredibly good at doing everything, even saying what they're feeling, but if they're not like really feeling it, if consciousness itself somehow, I don't think it is, but it's tied to this gloppy, gray, crenellated thing inside of our heads not being messed with.
Yeah, and of course, the whole problem is we don't have any principles by which to decide is an arbitrary physical system conscious or not? What is the character of its conscious experience? And people fiercely debate those questions, right? So Nick Bostrom, who wrote this very influential book on superintelligence a decade ago, had a striking phrase. He said, it could be that we will create an AI utopia, or what looks like one, with all of these, digital beings, living wonderful lives, but, they'll happen not to be conscious. And he said, it'll be like a Disneyland with no children, right? And how would we know?
Exactly. Yeah. How would we know? Because obviously we can't even tell whether each of us are conscious. I mean, I assume that you are. You assume that I am. I think we both make the reasonable assumption that we are. And I do wonder, though, are we placing too much value on having an inner world simply because we have one? Might it be that this world, this Disneyland world of AIs that are doing all this wonderful stuff without that inner sensation, why is that any worse than the world that we are familiar with?
Well, I mean, once you start asking these questions, you're on a very slippery slope. You can say, if no one has to be experiencing any of it, why does it even have to physically exist? Why isn't it enough that someone has written down an equation that implicitly contains all of these happy
Yeah.
digital beings in their Disney world? And of course, all the way at the bottom of that slippery slope stands Max Tegmark, waiting to welcome you, right? It's saying, just anything that you can mathematically describe, it's as good as if it's physically exists, and is being experienced. So I think, these are profound questions, and all we can do is look, a little bit ahead from what we've
Yeah.
actually experienced, and try to get things right as far ahead as we can foresee.
Yeah. Let me end with one profound question that I think we somewhat differ on, and I thought it might be interesting just to have a few words between us on. I used to think that mathematics is not quite as extreme as Max Tegmark, but I definitely used to think that mathematics was really out there. It was the reality that we were fumbling to try to reveal by, peeling back the layers that were obscuring the deep mathematical truths of reality. And over the decades, my perspective has radically shifted, not immediately, but it was a gradual shift that led to a radically different perspective where I'm now quite the opposite. I really think that all of this stuff is we humans seeing patterns, coming up with a language called mathematics that can encapsulate those patterns. We come up with mathematical models to describe the patterns of physical happenings and so forth. And so to me, it's all just like a human construct, which to me even makes it more wondrous than if it were actually out there. But where do you come down?
Well, let me get
on
down to brass tacks. I mean, suppose that we meet an extraterrestrial civilization. Do you think that they'll have the concept of prime numbers, and will they agree with us that 7 and 13 are prime and that 9 is not?
Yeah, good question. And here's what my response would be. They may not have a concept of prime numbers, but I do think that if we teach them
Mm.
this concept that we came up with,
Mhm.
that then they could follow the
Mhm.
reasoning and agree with us that 7 is prime and
Mhm.
13 is prime. So from that perspective, I'm not saying that any mathematical result can differ from, say, one civilization to another. But what I would say is when all thinking creatures are gone
Mhm.
in the far
Mhm.
future of the universe and it's just particles
Mhm.
floating through the void, I don't think the concept of prime continues to exist. I think it only exists within the
Mhm.
minds of conscious beings that for one reason or another find the concept useful
Mhm.
or interesting.
So I confess that I always have trouble seeing what is at stake in that debate, right? Like, what does it mean for
Mm,
primes to exist? No one believes that there's like a Platonic heaven that you can literally go to where you see 7 and 13 dancing around, right? But I would go a little bit further than you. I would predict that if we meet these extraterrestrials, not only will they agree with us about what is prime, I think they will have the concept of primes because it is so central to just, the structure of thought itself once you start thinking quantitatively at all. I mean, I'm
yeah,
sure that their mathematics will have developed in many different directions than ours has, but there are concepts that are so basic that it's hard for me to see why how they couldn't be rediscovered. And in fact, in human
yeah,
history, we've seen that mathematical concepts were discovered independently in China, in India, in Mesopotamia, or more recently on either side of the Iron Curtain. Right. So, and you could say, oh, well, it's because we're all humans, but I think it goes deeper than that. We're all trying to understand the same reality. We're all using the same laws of logic. And I think that alone actually determines a lot of this. In
yeah.
fact, I think even if we were to somehow meet beings in a different universe governed by completely different laws of physics, they would have a lot of the same mathematical concepts that we would.
Yeah. So I guess my view of that is I allow for the possibility. And if you push me hard on this, I will find it difficult to be
Mm,
specific. And that's where I feel that it's
mm,
tough for me to be
mm,
dogmatic here. But I do allow for the possibility that this extraterrestrial civilization will have such different
mm,
beings, such different life forms with such different sensory experiences, tapping into such different qualities of reality, maybe qualities of reality that we have absolutely no capacity to know about because we don't interact. Our material form doesn't interact. And because of that, they analyze the world in different ways, different kinds of patterns that may not even be mathematical patterns. I can imagine them looking at our textbooks and saying, math, yeah, we tried that in the early eons of our civilization, but now we realize that you need to go beyond that to this radically different framework. And if that's the case, I can imagine that math ultimately is viewed as something that is a tool developed for certain applications. And when there are other applications using radically different data, it's just not the language that we find useful.
Well, look, I mean, humans have many, many subjects that we like that are not mathematics, right? We have music, we have art. And it's very easy for me to imagine that these aliens will not have music or art as we know it. They will instead have something totally alien to us, being aliens, right? It is, but the beauty of math, since the time of Euclid, is that you can start with such simple axioms and then build everything else from that, right? So what I would ask you about this is, I can't rule out any of the things you're saying, but I would ask, do the aliens agree with us about, the law of the excluded middle? Do they agree with us about the basic rules of logic? Do they agree with us about the positive integers? And, if you'll just grant me those very minimal things, then I can argue you into agreeing that they're also probably going to have complex numbers.
No, that I all agree with.
Too.
But again, I would come back to that. I do think it's likely that if we explain these concepts to them, if they don't have them, that they'll be able to get on board. So from that point of view, there's an agreement. But again, whether these concepts have any relevance to the way they look at the world, that is a big question mark for me. And again, the bigger one for me is when all the thinking structures are gone, when there's nobody thinking at all, and it's truly just particles wafting through an ever expanding cosmos that's getting ever colder, whether these concepts still somehow are there, that's the one that really feels unlikely to me. Anyway, I think we covered, those questions as probably as far as we're going to go. These are fascinating mathematical, physical, philosophical questions, which ultimately I think people will argue about for a long, long time to come. But in any event, thank you again, Scott, for spending so much time with us today. A fascinating conversation, and look, let's see where this all goes.
Yes. Well, thank you. I mean, the Elegant Universe had a big impact on me when it came out, and it's an honor to do this podcast with you.
Well, thank you so much.
Yeah.
Thank you. Bye.
Okay, bye.